Hello everyone, this week we're going to learn about super vector machines and neural network, two advanced classification methods. We use Python's scikit-learn library to implement both and compare how they perform. Let's start with the import. Alright, so the first thing we do is import all the libraries we use. Let's start with pandas. This handles our data, making it easier for us to work with tables and datasets. Train test split is to split our data into training and testing sets, so we can train a model on some data and test it on data that it hasn't seen yet. SVC or support vector classifier basically is the SVM implementation from scikit-learn. This is what actually builds our SVM model. MLPClassifier or multi-layer perceptron, which is scikit-learn's neural network. MLP is just a fancy name for a basic neural network. Then we have our evaluation metrics like confusion matrix, accuracy score, and classification report. These tell us how well our models performed, like giving them a grade on their predictions. So here we have a small dataset with 12 people. We have two features, age and salary. These are what the model uses to make the predictions. And we have the target variable as purchase, either 0 for no or 1 for yes. This is a binary classification because there's only two possible outcomes. We convert this into pandas data frame so it's easier to work with, and in the code you can see df.shape gives us 12,3, meaning there are 12 rows and 3 columns. Next, we split our data using train test split. X is our features, age and salary. This is what we use to make predictions, and Y is our target, which is purchase, and that's what we're trying to predict. We do 75-25 split. That means 75% of our data is for training and 25% is for testing. So the model learns from 9 people and then it tests on 3 new people that it hasn't seen. The random set is set to 42. It just means that every time we run this code, we get the same split for consistency. Now we create our SVM classifier using SVC. Kernel equals linear means that we're using a straight line as our decision boundary because it's the simplest approach. C equals 1 is the regularization parameter. It controls how strict the model is. If C is small like 0.01, the model is too flexible and it might underfit. That means it's too chill about making mistakes. If C is large like 100, it tries to classify every single point perfectly and it might overfit because it's too strict, making C equals 1 a balanced middle ground. After that, we fit the model. That's the training step where it learns from our training data. And after that, we predict it on the test data. And these are the model guesses for the 3 test people, which is 0, 1, 0. Now we evaluate how well the SVM actually did. The confusion matrix shows us true negatives, false negatives, and true positives. In our case, we got 2, 0 and 0, 1, meaning 2 true negatives and 1 true positive, making it have no mistakes. The accuracy is 1.0, meaning 100%, so the model got everything right. The classification report breaks it down even further with precision, recall, and F1 score. Precision is 1.0, that's when the model said someone would purchase, and it was always right, no false positive. Recall is 1.0, meaning the model caught all the actual purchasers, no false negatives. F1 score combines precision and recall, and it's also 1.0, meaning a perfect balance. This is pretty much a perfect model, but keep in mind we only have 3 test samples, so it's a really small test set. Alright, now for the neural network using MLPClassifier. The hidden layer size is set to 5, meaning we have 1 hidden layer with 5 neurons. Think of it like this. Input data goes in, it passes through 5 neurons that process it, and then it gives us the output. You can do multiple layers like 5, 3 for 2 hidden layers. Meaning input data goes in, passes through 5 neurons, then 3 neurons, then you get the output. Activation equals ReLU is the activation function. It stands for a rectified linear unit. It helps the network learn nonlinear patterns, basically more complex relationship in the data. Solver equals Atom is the optimization algorithm. Atom is a really popular one because it's efficient and it is just learning automatically. Max iteration equals 1000 means it trains for up to 1000 iterations. That's how many times it goes through the training process. And then we fit it on the training data just like we did on the SVM. Now let's compare the predictions side by side. On the left, you see SVM predictions, which is 0, 1, 0, and it got all 3 test cases right, putting the accuracy at 1, which is 100. The neural network prediction is 0, 0, 0, meaning it missed 1 purchaser, making the accuracy 0.66. This shows that SVM is usually better for small datasets, and SVM creates clear decision boundaries even with limited data. Neural networks are more powerful for complex patterns, but they need lots of data to train properly. With only 12 samples, the neural network just don't have enough to learn from. After that, we tried to improve the neural network by changing parameters. We increased the hidden layer sizes to 100 neurons instead of 5, meaning it has way more processing power. And the max iteration is set to 2000 instead of 1000, giving it more time to learn. But look what happened. The accuracy dropped from 66% to 33%. It predicted 111, meaning that it said everyone would purchase. Actually, the real data is 010, so I got 2 out of 3 wrong. This is actually worse than before. It went from 66% to 33%. Now, why did this happen? It's probably because of overfitting. With 100 neurons and only 12 training samples, it's like having a massive brain with almost nothing to learn. It memorized the training data, but it can't generalize to new data. This really shows that you can't just throw in more neurons at a problem and expect it to be better. You need more training data. So to wrap things up, the key takeaway from this week is that SVM is great for smaller datasets and it creates clear decision boundaries. Neural networks are powerful, but it needs lots of data and careful tuning. We learned how to implement both using scikit-learn, how to evaluate them with confusion matrices and classification reports, and how to compare different models to see which one works better for your specific problems. In this case, SVM was the clear winner with 100% accuracy, while the neural network didn't perform as well. But in real-world scenarios with thousands or millions of data points, neural networks often outperform SVM. That's it for this week.